Okay, today's section is solving polynomial equations. And we've been dealing with all different exponents in our polynomials, cubes, quartics, quintics, and even higher than that. So today we're going to solve some of those equations. We're also going to find the zeros of those polynomial functions and state the multiplicity of each. So let's get started. To solve polynomials, we have previously factored them, used the zero product property after we factored, and we have also graphed, be able to see them using our chart table to help us find the zeros. So on this example it says use factoring to solve. Now keep in mind you have your whole list of factoring options and they are all possibilities. So I'm looking at this trinomial and I see the first thing that I want to do is factor out the GCF. That GCF, greatest common factor, is x. Whoops, we're just a little large here, so I want to do that. Move it back down to workable. Alright, so let's take that x out, and that would leave us with 5x squared minus 12x plus 4. That gives us a trinomial. That trinomial now can be factored, and since the a term is not 1, we are going to factor using the factors of the first term, which are 5 and 1 only, so we can lock those in. So I'm going to get a 5x and a 1x. And then the factors of that last term, 4, are 1, 2, and 4. So 1 and 4, 2 and 2. So we have to put those in here as well and hope to get it to work. I'm going to use the 2 and 2 just because our rule has always been closer together, or closer the factors are, the more possibilities. So let's put the 2 and 2 in and see if we can get a 12 in the middle. We do inside, inside, and get 2x. Outside, outside, 10x. There's our 12. Let's make sure the signs match. If we make them both negative, I think we're going to be good. So let's make both those quantities negative, bring our x back down. So we now have it factored, and it is completely factored. We have no other possibilities to do on each of those quadrants. So now do the zero product property. So by doing zero product property, we're saying each of these things, the x sitting by itself, the quantity 5x minus 2, and the quantity x minus 2, all have to be set equal to 0. So over here, if x is set equal to 0, that's the easy one. It equals 0. If 5x minus 2 is set equal to 0, we solve that by taking the 2 to the other side, dividing by 5, and we get x equals 2/5. So x equals 2/5 is a solution. So let's circle that. Let's circle our x equals 0 from the first step. And last but not least now, we've got the 1x minus 2 also equals 0. So we add 2 to both sides, and we get x equals 2, which is our third solution. So we've got x equals 0, x equals 2/5, and x equals 2. So if we now go back and look at our graph, we should see 3 zeros, 3 x-intercepts, and let's just check to see if we're on target here. We got a 0, a 2/5, and a 2. So it checks. We're good. And moving on. So we can solve with our factoring still. Now, if x minus r is a factor that occurs m times in the factorization, so in other words, more than once, and it's going to occur in our polynomial. So remember, our polynomial we're just referring to as p. Then that r value is a root with multiplicity related to that polynomial. So a new vocabulary word here, and that is multiplicity. If it occurs more than once in our solution, it has multiplicity, multiple times. So it is related. All right, now, when r is a root with even multiplicity, then the graph of the related function will touch but not cross the x-axis at r, 0. You cannot tell the multiplicity of a root by the graph of the related function alone. So what it just said is you can't tell by looking at the graph whether we have multiplicity there just because it doesn't cross the axis. So keep in mind a couple of things. When r is a root with even multiplicity, the graph of the related function will touch but not cross the x-axis. So we're thinking it will touch it, so it might be coming down like this, but it will not cross it. And so then it'll probably go back up and do something else along the way. Okay? So here's an example that uses this. Use a graph, synthetic division, and factoring to find all the roots of x cubed plus 3x squared minus 4 equals 0. So if we had to do this to start with, in order to use synthetic, you actually need to see a root. In order to factor, we need something we can take out, and right now we look at that and there is no GCF or anything, and it's x cubed, so that's not really going to help much in our factoring. So we want to go to our graph. So let's go and graph. Okay, so here we're looking at an example of the graph of our function, which was x cubed plus 3x squared minus 4. It appears that we have roots by guessing, and that's all you're doing right now unless you're looking at a table, roots at a 1. Okay, that appears to be 1. And this one looks to be a negative 2. So we could use both of those in our work, right? So let's go back. We said it looks like it crosses at a negative 2 and a positive 1. So with that, we already used the idea of graphing. We can now use synthetic division to help us graph this. So I'm going to take that positive 1, if that's my root we learn, then it goes there. And now our coefficients of 1, 3, remember we're missing the x term, so we need a 0, and then the negative 4 would be our values you put in, carried down the first term, and now we multiply. 1 times 1 is 1. Add. 3 plus 1 is 4. 1 times 4 is 4. 0 plus 4 is 4. 1 times 4 is 4. Negative 4 plus 4 is 0. So we get a remainder of 0, which then means we're looking at the term x squared plus 4x plus 4 as one of the factors, along with, since we had the 1, that factor would have been an x minus 1. Now, keep working. We want to double check to make sure that this x squared plus 4x plus 4 is not done, or we want to check to see if it is done, but we know we can factor x and x plus 2 plus 2. So right now we graphed, we used synthetic, and it appears that we have completed our factoring. If that's the case, and we've completed our factoring, then we can check our work, and it says use a graph, synthetic division, and factoring to find all the roots. So right now, if I was to name the roots based on our factoring, we would have that positive 1 we saw, and we would have a 2 that happens twice. Multiplicity of 2. So knowing that, oops, you're right, we had a negative 2, because our points were positive 2, so our roots had to be negative, and I missed that, and there it was, caught it in the check. So when you finish, you just named all the roots. That's all you need to do. But we graph first, as we call it, maybe to get a cheat. What does it look like we have for a solution? And that's where we got these values. Whoops, these values. Okay. So when we got the negative 2 and the 1, We could then use synthetic to verify it, and from there, factor. So we used all three possibilities. Now, sometimes polynomials can be factored by using variable substitution. So, use variable substitution and factoring to find all roots. So as you know, we have factored with a lot of quadratics, second degrees. This one is fourth degree. We haven't factored too many things of fourth degree. So a little trick of the trade is if we let a equal that x squared, so we're going to rewrite this. So that would then mean our x squared would be a squared minus 5a and then minus 6 would be our new trinomial that we're working with. And notice this is a trinomial that's very simple, very plain, and actually now easy to factor. So let's go ahead and finish factoring. And we would get our a, an a term in our first slot. We would get negative 3 and negative 2 in the other two slots. And again, double check it. First times first, a squared. Outsides will give us negative 2. Insides gives us negative 3 for a total of negative 5. And last times last, ooh, we have a slight problem. It gives us a positive 6, and we need a negative 6. So I think we're going to have to erase our possibilities of 3 and 2 and probably go with the 1 and the 6. My eraser's just a little big. So let's erase those, and let's go with our other choice, which was 1 and 6. Now let's try it again and see if we get it. And now we need a negative on the end, so I think we're going to need more negatives, so I think this a will have to be our positive. So looking at the possibilities, here we go. First times first, a squared. Outsides will be negative 6a. Insides will give us that 1a, which gives us a total of negative 5a. And last times last gives us negative 6. So there we have it with the correct factoring. But remember, we didn't have a's in our answer, so we can't just say, you know, here's the roots. So you just say, well, our roots are negative 1 and 6. No, because we have to put back in that original. So by substituting right now, we would get x squared plus 1 is one of the factors, and x squared minus 6 is the other factor. So now those are the values that need to now be solved for 0. So in doing that one at a time, we'll get x squared plus 1 has to be set equal to 0. So then we know x squared has to be a negative 1. And when we take the square root of both sides, we've learned you can take the square root of a negative, but when we do, x equals, we'll get plus or minus. The square root of negative 1 is now I. Do the same thing over here for your x squared minus 6 set equal to 0. Solve that one. You've got x squared equals 6. You take the square root of both sides. In doing so, you get x equals plus or minus the square root of 6. 6 cannot be simplified, broken down, because there's no perfect square numbers factors in that. So we're looking at 4 solutions right now. Our roots are x equals plus or minus I, and x equals plus or minus root 6. They are not whole number roots in this case, and they're actually imaginary. So there we go, plus or minus 6 and plus or minus square root of negative 1, which we again liked to say was I, so we like that better. Okay, good job. So remember variable substitution, especially if you can't factor it right away or it has weird combinations. This was even powers, so hint. So roots and zeros. The real number r is a 0 of your function if and only if all the following true. And we've been working on these. R is a solution or a root. Okay. X minus r is the factor of the expression that defines the 0. So that means then when you rewrite it, r is your root. When the expression that defines your function f is divided by x minus r, the remainder has to be 0, which means it goes into it evenly, nothing left over. And last but not least, r is an x-intercept of the graph of f. All right, that's all we have for today. We should be good to go.